Our modern world, this vibrant tapestry of technology and innovation, is built upon materials wrested from the Earth. Consider the device you might be using to read this, the vehicle that transports you, the very structures that shelter us. All of them began their journey as humble minerals, forged in the crucible of our planet's deep past. These elements are the essential building blocks of civilization, the silent partners in our grand human enterprise. From the shimmering screens of smartphones to the resilient alloys of spacecraft venturing into the cosmos, our reliance is profound. Yet the Earth does not yield its treasures easily, and the quest to find new sources becomes ever more challenging, a grand cosmic game of hide and seek. The easily found deposits, those glittering veins of ore that once lay exposed upon the surface, are now largely stories from a bygone era. Humanity, in its relentless drive for progress, has meticulously gathered these surface offerings. Now, our search must delve deeper, plunging into the complex, enigmatic geology that lies miles beneath our feet. Imagine searching for a single, uniquely shaped grain of sand scattered across an immeasurable cosmic beach. That is the scale of our task. The Earth's crust is vast, its secrets held tight. We are prospectors on a planetary scale, seeking faint whispers of riches hidden within an immense three-dimensional labyrinth of rock and time. Traditional methods of mineral exploration, born from centuries of observation and intuition, have served us well. They are the bedrock upon which our understanding of ore deposits is built. Geologists, like patient scholars of the Earth, walk the land, hammer in hand, piecing together the planet's history. Yet these venerable techniques can be slow, arduous, and often incredibly expensive. The sheer volume of terrain to survey is daunting, a planetary expanse that defies easy comprehension. We need a new kind of vision, a sharper lens to penetrate the opacity of the Earth and illuminate the path to future discoveries. The old maps, while valuable, may not show us the way to these deeper, more elusive treasures. But here, the narrative of our quest takes a thrilling, almost science-fictional turn. We stand at the dawn of a new age of discovery, armed not just with rock hammers and compasses, but with the extraordinary power of computation. The digital revolution has gifted us tools of immense capability, tools that can perceive patterns invisible to the human eye. Imagine intelligent systems sifting through veritable mountains of geological data, listening for the faintest, most subtle signatures of buried mineral wealth. This is not mere fantasy. It is the unfolding reality of mineral exploration in the 21st century. We are empowering ourselves to become smarter, more efficient cosmic prospectors. To embark on this advanced quest, we must first learn to listen, truly listen, to the stories our planet tells. Scientists, acting as cosmic detectives, meticulously gather a symphony of clues from the Earth. These clues are diverse, painting a multi-layered portrait of the subsurface world, a realm hidden from direct view. Our first informant is geology itself, the Earth's autobiography written in stone. Maps of rock types, the orientation of ancient fault lines, the history of volcanic activity, these all provide fundamental context. They tell us where certain mineral-forming processes might have occurred, billions of years ago, shaping the very ground beneath us. Each rock formation is a chapter in this immense terrestrial saga. Then, we deploy the tools of geophysics, allowing us to sense the unseen, to probe the depths without disturbing a single stone. Imagine sending pulses of energy deep into the Earth and carefully listening for the echoes that return. Magnetic surveys can reveal the presence of iron-rich minerals, their subtle pull betraying their location. Gravity surveys can hint at unusually dense regions, potential harbingers of valuable ore bodies. Electrical surveys map how well different parts of the subsurface conduct electricity, often a key indicator of metallic sulfides. Each dataset is like a different musical instrument, contributing its unique notes to the overall composition, helping us to understand the Earth's hidden architecture. High above our world, orbiting sentinels provide yet another crucial perspective. Satellites, our eyes in the sky, continuously scan the Earth's surface, capturing breathtakingly detailed remote sensing images. These images cover vast swathes of land, offering a synoptic view impossible to achieve from the ground alone. They can reveal subtle, almost imperceptible variations in vegetation health or soil composition. Sometimes a particular plant species might thrive or struggle over a mineralized zone. These faint patterns, spread across the landscape like clues in a planet-sized tapestry woven by geological forces over eons, can guide us towards areas of interest. And the story doesn't end there. Geochemistry adds another vital layer of information, like a forensic scientist examining trace evidence. Tiny, almost infinitesimal concentrations of specific elements in soil, stream sediments, groundwater, or even the leaves of plants can act as chemical breadcrumbs. These subtle anomalies, perhaps parts per billion, can indicate the presence of a much larger, more concentrated mineral deposit hidden nearby. Each sample carefully collected and analysed is a whisper from the deep, a chemical signature carried upwards from the Earth's interior. It's a delicate art interpreting these faint clues, but they can lead us directly to the source of the treasure. We find ourselves then with an extraordinary collection of data, intricate geological maps, cryptic geophysical anomalies, vast satellite images, and subtle geochemical signatures. It is a symphony of information, a rich but complex chorus of planetary signals. But how do we discern the coherent melody of a mineral deposit within this overwhelming cacophony of data? How do we pinpoint the precise locations where these diverse clues converge to tell a story of potential riches? This is the moment where machine learning steps onto the grand stage of exploration, offering its unique and powerful capabilities. It is a tool perfectly suited for this cosmic data challenge. Think of machine learning algorithms as incredibly astute, tireless apprentices. We don't program them with explicit rules for finding minerals. Instead, we train them by showing them countless examples. We present them with areas where valuable deposits have already been discovered, along with all the corresponding geological data, geophysical data, and geochemical data for those locations. The algorithms, through complex mathematical processes, learn to recognize the subtle, often non-obvious patterns and correlations that characterize these known mineral occurrences. They learn the fingerprint of a deposit, a signature woven from many different threads of evidence. Imagine teaching a computer to see the Earth's subsurface with the discerning eye of a seasoned geologist, but amplified by the ability to process and integrate information at superhuman speeds. These algorithms can simultaneously analyze dozens of different data layers, even hundreds of different data layers, far more than any human mind could effectively juggle. They can detect faint, complex interrelationships between these layers, how a particular magnetic signature might correlate with a specific rock type and a subtle geochemical anomaly, for instance. These are the hidden connections that often hold the key to discovery, connections that might elude human perception amidst the sheer volume of data. The workflow for this intelligent prospecting typically involves several crucial steps. First comes comprehensive data collection and meticulous preparation, gathering all those diverse clues from the Earth and ensuring they are in a usable format. Then, feature selection, which is like an expert deciding which types of clues are most diagnostic for the specific kind of mineral deposit being sought. The heart of the process is model training, where the algorithm learns from past successes. Finally, the trained model makes predictions on new unexplored areas, generating prospectivity maps that highlight zones with the highest potential for discovery. These predictions are then rigorously validated by geologists, combining artificial intelligence with human expertise. The implications of integrating machine learning into mineral exploration are nothing short of transformative. One of the most immediate and compelling benefits is the dramatic acceleration of the discovery process. What might have taken years of painstaking fieldwork and speculative drilling can now be significantly streamlined. Machine learning allows exploration companies to rapidly screen vast territories and focus their precious resources, time, money, and human effort on the most geologically promising targets. This efficiency not only speeds up the journey from raw data to potential discovery, but also helps to reduce the overall environmental footprint of exploration activities. It's simply a smarter, more targeted way to search. Beyond speed, there is the crucial advantage of enhanced accuracy. By systematically analyzing a multitude of complex datasets, machine learning models can often produce more reliable and nuanced prospectivity maps than ever before. These maps are not just pretty pictures, they are powerful decision-making tools. They guide geologists, pointing them towards specific areas where the statistical probability of finding a valuable mineral deposit is demonstrably higher. It's akin to being handed a treasure map drawn not by ancient pirates, but by a sophisticated artificial intelligence, one that has learned the Earth's subtle language of mineralization. This leads to better informed decisions and a higher success rate in drilling programs. However, this exciting journey into AI-driven discovery is not without its challenges. The performance of any machine learning model is heavily dependent on the quality and quantity of the data used to train it. For some rare types of mineral deposits, or in geologically complex regions, sufficient high-quality training data may simply not exist. Furthermore, many advanced machine learning models operate as black boxes. They can make astonishingly accurate predictions, but understanding precisely why they arrived at a particular conclusion, their internal logic or interpretability, can be difficult. For scientists and exploration managers, this lack of transparency can be a hurdle to full adoption and trust. Despite these hurdles, the future of machine learning and mineral exploration gleams with immense potential. Researchers are actively working on developing more explainable AI models, making their decision-making processes more transparent and understandable to human experts. New techniques are emerging that allow machine learning to be effective even in areas with sparse or incomplete data, pushing the boundaries of exploration into new, previously challenging frontiers. As these sophisticated algorithms continue to evolve, and as our ability to gather ever more diverse Earth data expands, our capacity to responsibly unlock the planet's hidden mineral wealth will undoubtedly grow. The cosmos of discovery, right here on Earth, still holds untold wonders for us to find.